This is the video lecture for Part 1 of Section 3.2, Basic Properties of Rings. We're going to first look at arithmetic in rings. And using the axioms of a ring, we can show that many of the properties of arithmetic in Z also hold in any ring. In order to prove any new properties, we can only use the ring axioms and any previously derived properties. We want to start by showing that the additive inverse of an element in a ring is unique. This will enable us to introduce a notation for the additive inverse and to introduce the operation of subtraction. So this is Theorem 3.3. For any element A in a ring R, the equation A plus X equal the additive identity 0 sub R has a unique solution. That is, for each A in R, there exists a unique N in R such that A plus N equals 0 sub R. To prove this, we'll suppose A is an arbitrary element in R. Then by axiom R5, which is existence of additive inverses, there exists an element N in R such that A plus N equals 0 sub R. It remains only to show that the element N is unique. So axiom R5 in the definition of a ring tells us that there exists an element N satisfying this equation, but we need to show that the element N is unique. So we'll do a typical uniqueness proof. We'll suppose that we have another element that satisfies the same condition. So suppose n prime in R is an element that satisfies the same condition, namely that A plus n prime equals 0 sub R. We then need to show that n is equal to n prime. Now note that at this point in our study of rings, the only tools at our disposal are the axioms in the definition. So we want to justify each of our steps using only the axioms and the hypotheses in the theorem. So we'll start with n and show that it equals n prime. So n is equal to n plus 0 sub R. This follows by axiom R4. And this is equal to n plus the quantity A plus n prime. And this is by our hypothesis that A plus n prime equals 0 sub R. And this is equal to the quantity n plus A plus n prime. This is using the associative law of addition, which is axiom R2. And this is equal to A plus n quantity plus n prime. This is using the commutative law of addition, which is axiom R3. And then A plus n is equal to 0 sub R, so this is 0 sub R plus n prime, and that's by our other hypothesis that A plus n equals 0 sub R. And then this is n prime plus 0 sub R. That's the commutative law of addition one more time, axiom R3. And finally, this is equal to n prime. That's axiom R4. So we've started with n and we've ended with n prime. So therefore, n is equal to n prime, which proves the equation A plus x equals 0 sub R has a unique solution. And this proves the theorem. Now as a remark, the unique solution to the equation A plus x equals 0 sub R is denoted minus A and is called the additive inverse of A. So minus A is the unique element of R for which A plus minus A is equal to 0 sub R. For an example, we can find the additive inverses in Z7, which consist of the integers mod 7, 0 through 6. And 0 plus 0 equals 0. So this tells us that minus 0 is equal to 0. So 0 is what you add to 0 to get 0. 1 plus 6 is equal to 0. So 6 is what you need to add to 1 to get 0. So this tells us that minus 1 is equal to 6. The additive inverse of 1 is 6. 2 plus 5 is 0, so minus 2 is 5. 3 plus 4 is 0. So minus 3 is 4, and so on. 4 plus 3 is 0, so minus 4 is 3. 5 plus 2 is 0, so minus 5 is 2. And 6 plus 1 is 0, so minus 6 is 1. So to determine the additive inverses, we need to ask, what do we add to the element to give us the additive identity, which is 0? Now, we can now define subtraction in a ring for any elements A and B in R by B minus A is defined to be B plus minus A. So we take B and we add the additive inverse. For an example, we can evaluate 1 minus 2 and 2 minus 5 in Z7. Well, 1 minus 2 is equal to 1 plus minus 2, according to our definition of subtraction. And minus 2 is the additive inverse of 2 in Z7, which is 5. So this will be 1 plus 5, which is equal to 6. 2 minus 5, this will be 2 plus minus 5. And this is equal to 2 plus 2. The additive inverse of 5 will be 2. And 2 plus 2 is 4. Now the next two theorems show that many of the standard rules for arithmetic operations involving negatives and subtraction of integers apply in any ring. To prove these, we can only use the ring axioms and previously proved results and cannot rely upon our knowledge of the operations in Z. So many of these rules will look familiar to us because we're used to using them in Z, but here we're going to prove them in an arbitrary ring, and so we can't use our prior knowledge of the operations in Z. So first we have Theorem 3.4, which is called the cancellation property. And this states, let R be a ring for all A, B, C in R. If A plus B is equal to A plus C, then B is equal to C. So if we have the same element on both sides of an equation, we can cancel it out. So for the proof, we're going to suppose A, B, C, and R are arbitrary. We'll suppose our hypothesis that A plus B is equal to A plus C, and we need to show the conclusion, B is equal to C. So we can start by adding minus A, the additive inverse of A, to both sides of the hypothesis. So this will be minus A plus the quantity A plus B is equal to minus A plus the quantity A plus C. Next, we can rearrange our parentheses using the associative law of addition. So this will be the quantity minus A plus B equals the quantity minus A plus C. So that's axiom R2. And then minus A plus A will be 0 sub R. And so this will be 0 sub R plus B equals 0 sub R plus C. That's using axiom R5. And then finally, 0 sub R plus B will be equal to B, and 0 sub R plus C will be equal to C. That's our axiom R4. So this proves the theorem, and therefore our cancellation property holds. Next we have Theorem 3.5, and this says for any elements A and B of a ring R, okay, we have 7 parts to the theorem. So the first part says that A times 0 sub R equals 0 sub R, and this is also equal to 0 sub R times A. So when you multiply the additive inverse times any ring element, you get the additive, whenever you multiply an element times the additive identity, you get back the additive identity. 2 says A times minus B is equal to minus the quantity AB, and this is also equal to quantity minus A times B. So if you have the product of two elements and one of them has a minus in front, or is the additive inverse of the element, that's going to translate to a minus in front of the product itself. For 3, we have minus A is equal to A. 4 minus the quantity A plus B is minus A plus minus B. 5 minus the quantity A minus B is minus A plus B. 6 minus A times minus B is equal to AB. So when you multiply two negatives together, they cancel one another out and you get a positive, is one way of thinking of it, although A and B don't necessarily have to be positive to begin with. And then 7 says if R has an identity, then minus 1 sub R times A is equal to minus A. So if the ring has a multiplicative identity 1 sub R, then minus 1 sub R times A is minus A, the additive inverse of A. So for the proof now, we'll start by supposing A and B are arbitrary elements in R. And then we need to show that each of 1 through 7 hold. So we'll start with 1, and we'll show just the first equality, that A times 0 sub R is equal to 0 sub R. So by axiom R4, 0 sub R is equal to 0 sub R plus 0 sub R. It follows from the first distributive law in R8 that a times 0 sub r will be equal to a times 0 sub r plus 0 sub r, which will be a times 0 sub r plus a times 0 sub r by the distributive law. Now by axiom R4, a times 0 sub r will be equal to a times 0 sub r plus 0 sub r. So now we have two equations for a times 0 sub r, and setting these two expressions for a times 0 sub r equal, we obtain a times 0 sub r plus a times 0 sub r equals a times 0 sub r plus 0 sub r. Okay, now we can apply our cancellation property, because on both sides of this equation we have a times 0 sub r. So theorem 3.4 now implies that a times 0 sub r equals 0 sub r, and that's what we needed to show. Now the proof of the second equality, 0 sub r times a equals 0 sub r, will be similar to this. Next we have property 2, a times minus b is equal to minus quantity ab is equal to minus a times b. So now by definition, minus the quantity ab is the additive inverse of ab. That's what that notation means. When we put a minus in front of an element, we're saying that that is equal to the additive inverse of that element. So the first equality, a times minus b equals minus ab, says that the additive inverse of ab equals a times minus b. Since the additive inverse is unique, if we can show that a times minus b behaves like or has the property of the additive inverse of ab, meaning that ab plus a times minus b equals 0 sub r, then it must follow that a times minus b is the additive inverse of ab. Okay, so to prove this equality, we want to show that the additive inverse, or we want to show that a times minus b is the additive inverse of ab. Now, since the additive inverse is unique, if we can show that a times minus b behaves like the additive inverse of ab, that will tell us that it must be the additive inverse of ab. So if this sort of quacks like the additive inverse and walks like the additive inverse, it must be the additive inverse. And what we mean by behaves like the additive inverse, we mean that it satisfies the equation shown, that ab plus a times minus b is equal to 0 sub r. It's what you have to add to ab to get the additive identity 0 sub r. So the whole proof relies upon proving this equality. So to prove the equality, we'll start with the left side. So ab plus a times minus b is equal to a times the quantity b plus minus b. This is by axiom R8, the distributive laws, one of the distributive laws. And b plus minus b is equal to 0 sub r. That's by axiom R4, that's by axiom R5. That's a typo there. And then a times 0 sub r is going to be 0 sub r. And that's by part 1 of our theorem. We just got done proving that a times 0 sub r is equal to 0 sub r. Okay. So we've proved the equality, so therefore a times minus b behaves like the additive inverse of ab. So I forgot the word of there. So must be the additive inverse of ab. And so thus a times minus b is equal to minus ab. Now the proof of the second equality, minus ab equals minus a times b, will be similar. Now for property 3, we want to prove minus a is equal to a. So two negatives cancel one another out, basically. Now by definition, minus a is the additive inverse of minus a. So this equality says that the additive inverse of minus a equals a. So to show this, we can show that a behaves like the additive inverse of minus a, meaning minus a plus a equals 0 sub r, meaning that when we add a to minus a, we get the additive identity, 0 sub r. Since minus a is the additive inverse of a, then we know that a plus minus a is equal to 0 sub r. Now by axiom R3, the commutative law of addition, this implies that minus a plus a equals 0 sub r, which is what we needed to show. And therefore a behaves like the additive inverse of minus a, so must be the additive inverse of minus a. So thus, minus minus a is equal to a. So this is the same type of reasoning used in property 2. To show that something is the additive inverse of an element, we want to show that it behaves like the additive inverse of the element. Next we have minus the quantity a plus b equals minus a plus minus b. And to show this, we can once again use that idea and show that minus a plus minus b behaves like the additive inverse of a plus b, meaning a plus b quantity plus the quantity minus a plus minus b equals 0 sub r. So to prove this, we'll start with the left side. So a plus b plus the quantity minus a plus minus b, this will be equal to a plus the quantity b plus a plus minus b. So what we've done there is we've just rearranged parentheses or brackets, and this is using the associative law of addition, which is axiom R2. Now inside the brackets on the right side, we're going to rearrange the order of the terms, and so this will be a plus the quantity minus a plus b plus minus b. So this is the commutative law of addition R3. And then we'll rearrange parentheses or brackets one more time, and this will be quantity a plus the quantity b plus minus b. So that's the associative law of addition R2. And then a plus minus a is 0 sub r, and b plus minus b is 0 sub r, and this is by axiom R5. And finally, 0 sub r plus 0 sub r will just be 0 sub r, which is by axiom R4. So we've proved our equality, and thus minus the quantity a plus b is equal to minus a plus minus b. For property 5, we have minus the quantity a minus b is equal to minus a plus b. And the proof of this equality will be similar to that for 4. We can show that minus a plus b behaves like the additive inverse of a minus b by showing a minus b quantity plus the quantity minus a plus b is equal to 0 sub r. Next is property 6, which is minus a times minus b is equal to ab. Now the proof of this one will be a little bit different than the previous proofs. So we'll start with part 2 of the theorem. Now part 2 of the theorem states that a times minus b is equal to minus the quantity ab, and minus a times b is minus the quantity ab. So there are two equalities in part 2, and so these are the two equalities sort of written separately. Now applying the second equality with b replaced by minus b, we obtain minus a times minus b on the left side, and then on the right side we'll have minus the quantity a times minus b. So part 2 holds for any elements a and b, and so we can certainly apply that equality in part 2 with b replaced by minus b. Now by the first equality in part 2, the right side of this equality is, it's minus the quantity a times minus b. That's going to be equal to minus minus ab. So that's just replacing the a times minus b in the brackets with minus the quantity ab. Now by part 3 of the theorem, the right side of this last equality is going to be minus minus ab is just ab. Okay, so going back to our first equation, we have minus a minus b on the left side, and that's equal to the left side of our second equation, which is then equal to the right side of our third equation. So sort of following the chain of equalities, we obtain minus a times minus b is equal to ab as required. Okay, and now finally we have property 7, which states if r has an identity, a multiplicative identity, then minus 1 sub r times a is minus a. And so let's suppose that R has a multiplicative identity, 1 sub R, and we need to prove this equality. Minus 1 sub R times A is equal to minus A. So by part 2 of the theorem, minus 1 sub R times A will be equal to minus the quantity 1 sub R times A. And 1 sub R times A is just A, so this will just be minus A. And that's what we needed to show. So this is a fairly quick result. So this completes the proof of the theorem. Now, we're going to talk a little bit about notation, and we can use the same notation used for repeated multiplication and repeated addition in the integers in any ring. So if we let A be an element of a ring R and let n be a positive integer, we then define A to the nth power to be A multiplied times itself n times. So we have a product of A's with n factors. Now it's straightforward to verify that for any two positive integers m and n, we have our rules of exponents, that a to the m times a to the n will be a to the m plus n, and a to the m raised to the nth power will be a to the mn power. Now if R has an identity, then we define a to the 0 to be the multiplicative identity 1 sub R. And with this definition, the exponent rules will hold for all non-negative integers m and n. Now, if we again let A be an element of a ring R and let n be a positive integer, we define NA to be A added to itself n times. So that's A plus A plus A with n terms, or n sum n's. Minus n times A will be minus A plus minus A added to itself n times. And we also define 0A is equal to 0 sub R. Okay, so in this equation now, 0 on the left-hand side is the integer 0. 0 sub R on the right-hand side is the ring's additive identity element.